Solve the following system of nonlinear equations algebraically. 2x squared plus 3y squared equals 5. 3x squared minus 4y squared equals negative 1. In this situation, I have two equations. They both sort of look like circles, but the coefficients are different in the first equation, and the coefficients on your x squared and your y squared have to be equal for a circle equation to be made. So this is actually more like an ellipse, okay, an oval shape. The other one's a bit different because it has this minus between it. This turns out to be what's known as a hyperbola. And a hyperbola is a strange looking shape. It could potentially open upward or downward, but it sort of looks like two different parabolas that go toward these oblique asymptotes toward infinity. You don't really need to know any of that. But if you did, then what you could potentially determine is if you had an ellipse then, and I don't know if this ellipse is wider on the x or wider on the y, it doesn't really make a difference. I'm just kind of thinking outside uh, what the number of potential solutions might be, which looks to me like it could be up to 4 solutions. So let's see what happens when we try and solve these. Now, normally with the nonlinear systems, I try and push the use of substitution. But if all the variables are squares, then it's sort of the same system of solving if you're using elimination. So it's perfectly fine to use elimination in that case, in my opinion. What we would need to do, however, is multiply the top equation, let's say by 4. So I'll say 4 times 2x squared plus 3y squared equals 5. And the bottom equation by 3. So 3x squared minus 4y squared equals negative 1. So what happens there is we end up with 6x squared plus 12y squared equals 20. And the next one is 9x squared minus 12y squared equals negative 3. So when I add these two equations together, the y variable will cancel out. That's what I wanted to happen. So 9x squared and, oh, I'm sorry, this would be 8x squared, wouldn't it? 4 times 2, obviously. 9x squared and 8x squared would add to 17x squared. Then 20 minus 3 would be 17. Oh, and that's actually a lot nicer than what I had before because now the 17's cancel and I get x squared equals 1. And when I take the square root of both sides to get x by itself, of course I need to make sure to consider the positive or negative case. So x would be plus or minus 1. All right, so solutions. At this point, it looks like I have two solutions, one where the x value is positive 1, and another where the x value is negative 1. In order to figure out the y that is associated, I need to go back to one of these two equations, and it doesn't matter which one, and I need to plug in the x coordinate and see what I get. So let's see, when x is 1, if I plug into the top equation, because I don't think either one is easier than the other, I would have 2 times 1 squared plus 3y squared equals 5. So 1 squared is just 1, then times 2 is 2. So if I subtract 2 from both sides, you know what, I'll do it this way. So subtract 2 from both sides, and that gives me 3y squared equals 3. Now I'm going to divide both sides by 3, so y squared equals 1. And when I take the square root of both sides, y equals plus or minus 1. So when x is positive 1, y is positive or negative 1. So there's actually two solutions there. So when x is positive 1, y can be positive 1. But when x is positive 1, y could also be negative 1. Now, when x is negative 1, the same sort of thing is probably going to happen. Because if you'll notice, when I plug in negative 1, nothing really changes here. Because negative 1 squared is 1, positive 1, times 2 is 2, so if I subtract 2 from both sides, I end up with 3y squared equals 3, which is the same place that I ended up above here, so what's going to happen is, well, I should show those steps, I suppose. When I divide by 3, I get y squared equals 1, or y equals plus or minus 1. So I can have x is negative 1, y is positive 1, and when x is negative 1, y could also be negative 1. So there were a total of 4 solutions here.